Now let us solve an example. The example problem says that slurry composed of 3500 kg of water and 1500 kg of kaolinite at 35 degrees centigrade 1 bar pressure has to be centrifuged. The powder has normal particle size distribution mesh between 0 to 100 micron with 10 intervals. The powder is having standard deviation of 5.227 micron. Its D50 has also been given. The first problem is using perforated basket centrifuge of diameter 0.9 rotating at 1000 rpm. The filter cake medium resistance is given with porosity and average sphericity. They are also given. We have to estimate the residual moisture, filter cake resistance, and average diameter of the particles in the cake. So that is the first problem. We will see the other problems later. So let us first do this perforated basket centrifuge simulation. And one thing you remember that we have only one stage diameter, okay? So this is only one basket dimension it has been given. So it is a simulation problem. It is not a design problem. So let us kaolinite let us rename it, and then water. So kaolinite is suspended in water. Let us use solids model. Okay, before that we have to set it as solid. Method specification, let us use solid specification. And then run. Okay, the properties done. Let us go to the simulation window. We have to take this centrifuge over here. Material stream. This is feed. This is liquid. This is solid. Again, rename it. Feed. Liquid. And solid. So global it is mix CLPSD. This is normal. Let us see once again. This is kaolinite powder has normal PSD between 0 to 100 micron with 10 intervals, right? So it is equidistant, 10 intervals, 0 to 100 micron. Create PSD. It is done. Now go to feed. It is 35 degrees centigrade, 1 bar pressure. So 35, 1 bar. And we have 1500 kg of kaolinite and 3500. So it is mass flow 3500, and here it is it is 1500. It is 35 and 1 bar. Particle size distribution. So it is distribution function, which is normal. Standard deviation is given 5.227. So this is 5.227 and 8.343. So it is 8.343, both micron. Okay. So it has been calculated. Now, although it is spread from 0 to 100, but I think all the particles are between 0 to 30 micron. Above 30 micron, there is hardly any particle. And that is obvious because its standard deviation is very less. Mean diameter is also very less. Now let us use a perforated basket centrifuge. So okay, so this is the perforated basket centrifuge having diameter 0.9 and 1000 rpm. So this is 0.9 meter and 1000 rpm. It is not in design mode, so we'll keep it like this. The ratios, we leave it as it is because we do not want to disturb that. Deliquoring model, estimate residual moisture or specify residual moisture. Now, I think they have asked us to estimate the residual moisture. Fine. So, we'll not specify anything. Keep it like this. Solid cake, we have to provide the filter cake medium resistance, which is 10 to the power 10 per meter. So, it is 1E10. Any more information? Yeah, porosity and average sphericity 0.5, 0.45 and 0.75. So it is 0.45, 0.75. By default, it has been given. Okay, so all of them are done. So run the simulation. Okay, so it says that there is some warning. So let us see what is the warning. So it says that for all specified perforated basket configuration, the calculated maximum flow rate is less than the filtrate flow rate. It is required to meet the estimated or specified residual cake moisture. So calculation continued using best configuration. So whatever the calculation that is happening inside, it is saying that total flow is becoming 0. So in this problem, we are not able to meet the expected flow rate. So in my understanding, there will be some problem with the flow rate. There will be some problem with the ratio of flow rate of liquid and solid. So let us change the solid quantity let us decrease the solid quantity a bit. So instead of 1500, we give 150. Okay, and let us try it. No, still it is giving a problem. Let us change the porosity. Let us increase the porosity to, say, very high porosity. Let us give and run the system. No, still it's a problem. Let us give some filter cake specific resistance so that resistance decrease the flow rate so that the flow rate doesn't become 0. So we give, say, this much meter per kg and we run it. Now the simulation is done. Now, although we have tried with some random parameters, it is not actually advisable. You have to give proper data for successful simulation. But just to make this work, I have given these random parameters. So it may not give the best of the results, but let us see what results we have got. So go to the results section, summary. The particle diameter, it is 8.885. The basket height has been selected. Moisture content, we have got 22% moisture content. Okay, very high moisture content because we have reduced the solid content to 150 kg per hour, from 1500 to 150 kg per hour, while the liquid flow rate is still 3500. So 3500 is to 150. So the amount of liquid is very high. So the moisture content is also very high. So it is not acceptable in normal circumstances. Obviously, as I said, that you have to give proper information when you want a serious problem to do. And then let us go to the streams. And here you can see various information. The liquid fraction, solid fraction is given. Okay, so here you'll find that in liquid stream, it is completely liquid. There is no solid fraction. And in solid stream, all the solids have come over here in the solid stream. And high amount of liquid is there. And if you want to see the particle size distribution, you have to find over here PSD. It is understandable because we have only one solid outlet and all the solids have come through that outlet. So whatever the inlet particle size distribution, the outlet particle size distribution will be exactly same. So there is no prize in guessing that. So that's how the simulation stands. And as I said, that this may not be the best simulation because we have used some arbitrary random parameters. So it's okay. Now we change back to 1500 because we solve other problems. So the next problem is this. Use a decanter or disc centrifuge working with ideal separation. Deliquoring moisture content is 15% on wet basis. So this problem, we have to use either a decanter or a disc centrifuge. Now, why it is called decanter or disc centrifuge? Because for both of them, we have the same ideal separation problem. Okay, so let us choose a decanter model. Okay, decanter model with ideal separation and deliquoring model. So there we have to specify the residual moisture content. So residual moisture content is 15% on weight basis. So we have to give 0.15 on weight basis, and our specification is done. Let us run it. Yeah. So we have got the result without much problem. So let us see the results. So here you can find that it is ideal separation. So liquid load is given, the total separation grade. Total separation grade is 1 because, as you know, this is ideal separation. All the solids have gone to the solids, and you can see it in the result summary. Here also, in the liquid, there is no solid. Okay, and so the entire 1500 kg per hour of kaolin has moved to the solid stream. So this is the ideal separation. Okay, so in ideal separation, you know, Tx is equal to 1. Okay, so that's exactly what happens over here. And repeat the previous problem with ideal classification. Now for ideal classification, we need a cut size. No cut size has been given. Anyway, let us use a ideal classification. Now cut size has not been given, but we can assume some cut size. Let us take a cut size of, say, around 8 micron. Deliquoring model, leave it because all other things are same. Run it, and we can see the centrifuge results. Here the total separation grade is 50%, because we have seen this is the separation grade efficiency. We have chosen this point to be 8 millimeter. So Tx, we have set it the cut size over here. Now we can check the result stream. Here it is 50% over here, solid. And best thing is you can check the particle size distribution. Here you see, this is the particle size distribution. So anything beyond 8 micron, so I think we have taken a wrong cut size. Let us take a cut size of, say, 20 micron and redo the problem. Okay, so let us take 20 micron and redo the problem. Yeah, now this is understandable. So up to 20 micron, everything has gone to liquid stream. And above 20 micron, everything has gone to solid stream, because Above 20 micron, this is a cut size. Above 20 micron, everything has been filtered. Okay, so this has come to the solid stream. And below cut size, that has escaped through the liquid stream. That is how the solid separation works. Now let us go to the next problem. It says, repeat previous problem with square function classification with boundary particle size of 20 micron. Okay, so repeat this one with square classification with boundary 20, right? So instead of cut size, it is saying 20 micron. Yeah. So let us run it and check the result summary. So this is not the ideal separation. So you will see over here, whatever the solid material or solid particles are there in the liquid, they are all within this 0 to 10 micron. And 20 and above, all of them are over here in the solid section. And between 0 to 20, it takes a curve of this nature. If you remember, the curve is something like this, the square function curve. So this portion is represented by these numbers from 0.9 to 0.87. Okay? And above that, all of them are same, almost. And this will be more clear if we use the cut size of 25 rather. So let us do one more thing. Let us change the cut size from 20 to 25 and redo the problem. Yeah, that's exactly what I was expecting. The moment we take 25, then some more items are there in the liquid stream. So a major portion of 0 to 10 micron has come to liquid stream, and a portion of 10 to 25, it has come over here. Okay, so 20 onwards, the particle size distribution is something like this. Okay, so that's how the square function works. Now, next problem is decanter centrifuge with the following configuration. It is using Stokes classification, right? So we have to use Stokes classification. Right. So the moment we use Stokes classification, configuration has to be given. So configuration is drum diameter 1 meter, cylindrical length 3. So this is 1 meter, this is 3 meter. Okay, and then screw blade pitch 0.1, pond depth of 0.3. So screw blade pitch 0.1 and pond depth 0.3. Rotary speeds, drum and differential, they are 1550. So 1550 over here. Okay. Run. Okay. So results are available. Just go to see the results once again. This is 8.885 as usual. The residual moisture content 15%. The liquid load is 0.17. And we have again got the total grade efficiency to be 1. So all the solids have been separated. So just check the results. There is no solid over here. There is no solid. All the solids have come over here, and as expected, the particle size distribution of feed and particle size distribution of solid stream, they are same. Okay. And then use a disk stack type centrifuge with the following configuration. So the next problem will go to the disk type. So this is disk type. Scuba classification model it has asked. So we have to use some Scuba. If we use configuration with outer disk 10 and 3 inch, so it is 10 inch and 3 inch. And this is 3 inch. What else? Height of channel is 1 meter, angle of disk 45. Height of channel 1 meter, angle 45. Drum rotary speed 1000. So this is 1000. Okay. And scuba separation sharpness, nothing is said about separation sharpness over here, but let us use 0.5 say, or maybe 0.75. 0.5 might be very low. Okay, run it. Okay, so again, the separation grade efficiency 1, that means entirely it is going to the solid stream, nothing in the liquid. Okay, so these problems are set in such a way that the entire solid portion is going into the solid stream. So maximum efficiency. So in real life, such cases are not common. The next problem is pusher type centrifuge with plug and flow deliquoring model and square function classification with boundary particle size of 16 micron. So let us use a pusher type model. So this is the pusher type model with square function classification, particle size 16 micron. Deliquoring model is plug flow. Okay. Plug film flow, so you have to give the saturation factor and saturation exponent. They are 0.5 each. So this is 0.5 and this is 0.5. Waiting angle is 45 degrees. So waiting angle is here 45 degree. Then bulk flow resistance is 10 to the power 10 per meter square. So where is bulk flow resistance? I think it is over here, 10 to the power 10. So it is 1E10. Porosity is 0.05. So porosity is 0.05. What else? Pusher configuration is as follows: 0.5 meter drum dia, 10 meter drum length. So Drum die is 0.5. Drum length is 10. Five-inch stroke length and push frequency 10 per minute. 5 and 10. So 5-inch, it is 5-inch, push frequency 10 per minute. Okay. Then drum rotary speed 1000 rpm. Both sieve and product friction factor 0.5. So it is 1000. This is 0.5. This is 0.5. Okay, so everything has been fixed. Use 10 times the solid feed in this problem. So solid feed, actually we had taken 1500, right? Yeah, 1500. So take it 15,000. That's what it says, that in pusher we need lot of solid. So 1500 will be too less. Yeah. Okay. So the problem is set. We can run it. Yeah. So problem is run. We can see the results. This is the particle diameter. Residual moisture content is 25%. Cake height is 1.76 inch. The residence time is 29 hours. It's quite high. Total separation grade is 43%. So we have reduced the separation efficiency. Obviously, if we increase the solid flow 10 times, the separation will be lowered. Okay. Result summary we can see over here. So all the particles, they are in liquid stream. They are between 0 to 10 micron. And all the particles above 10 micron, they are over here in the solid stream. Okay, so this is the pusher type centrifuge problem. Okay, so that ends our example. So with that, we come to the end of this lecture. It has been a long session, but in this lecture, we have learned different types of centrifuges, their operating principles. We have seen some interesting animation through which we understood how the centrifuge works, and we have solved few example problems where different types of centrifuges have been simulated, and we have got some expected results. I hope you have enjoyed this session, and we will come back with yet another interesting session with interesting problem. Thank you.